Perfect. It's getting recorded now. So good afternoon, everyone. This is the third video recorded lecture of the lecture number 14 in this course, IC242 Continuum Mechanics. A quick feedback from your side. So you have seen videos 1 and 2, and based on that, is there any feedback in terms of how the video should proceed? Any content related change? Any feedback from your side? There's no critical feedback, so it seems that you're happy. What I realized was that after seeing the videos later, they seem to be a bit slow, because when we are looking at a video, then it's available. It's an option to pause and think about things rather than actually the video spending time in that sort. So this time, what I'm doing is I've already written something. It's like preparing slides, and we'll try to go through the slides and fill in the information as we work through it. So it's going to be a bit more condensed. So during this the lecture, when the people who are online, they may feel that it's a bit fast, but in case it's too fast, let me know. Otherwise, you can always visit the video and have a look at it. Because what I see is that most of the people are looking at videos, they are not attending the classes. So I only see 10 participants out of 130 students registered in the course. So probably the preferred mode of learning is through videos, not through online. But in any case, people who have joined, they're free to ask questions and give their feedback. Okay. So the agenda for today's discussion is going to be, first we'll do a quick recap. So we have been talking about stress tensor. So this is going to be the second lecture on the stress tensor. So today we'll start with a quick recap of what we have discussed till now in the last lecture, which was about the definition of what stress tensor is. Next, we'll start. So towards the end of the last lecture, I gave you a question to work by yourself, and that was to see if actually stress, the quantity stress, the stress matrix, is actually a stress tensor. Okay, so we'll do that today. So we'll show that the stress matrix is actually a stress tensor. Next, we'll work with force and moment equilibrium. So we'll try to take a body, we'll try to use the idea of the stress tensor, and we'll try to, given that the body is in equilibrium in terms of force and torque, we'll try to formulate the equations of motion for that body using our stress tensor. Okay? So force and moment equilibrium. Then towards the end, we'll quickly talk about stress transformation, so which uses the mathematical ideas of transformation of tensors that we have discussed, particularly for the stress tensor that we're talking about. Finally, we'll talk about the principal values and principal directions of the stress tensor in this particular application. Then last time there was a feedback saying that, can I please discuss the solution to the problems from lecture number 12, which was the last lecture in mathematical background on tensor calculus. So I can start with that solution, and then I can start with the stress tensor discussion. But before that, there are two announcements. So number one, we'll have the problem set 3 available by tonight. So the problem set 3 will mainly talk about tensor calculus. So you'll have questions from tensor calculus in problem set 3. And then another major announcement, which will also be emailed, and you're happy to give your feedback right now or later, is that we have a new evaluation pattern for this course. Now you already know that till 31st March, there's no coming back to the campus. And even the lockdown may extend to April, first few weeks. We don't know that yet, but the most probable guess is that it will get extended. So that means that having 2 quizzes doesn't make much sense, because we'll end up having the 2 quizzes in just within a week. So rather than that, I thought that we can have quiz 1 of 40% and the end sim will be 60%. But this is still under consideration. So if you have any feedback, you can email it to me, and we can discuss it. All right. So let's start. Let's start with the solution to the problem from lecture number 12. I gave you two problems. The first one, we discussed it to some extent. It was a simple application of the Gauss divergence theorem. I will not go through it because it's a straightforward application of the Gauss divergence theorem. So I expect you to do it by yourself. Now the other one is what I discussed today, is this one on the screen. So it says that using the initial notation, you have to show that this integral on the left hand side, which is a surface integral, is equal to 6 times the volume of the object. So let's do that. Okay, let's check if this is correct. Yeah. Right. So the integral is the gradient of the dot product between the position vector x, the whole thing dotted with n hat, and this quantity is integrated over the surface area of the body. So if you have a body and it has a surface area gamma, well, the closed surface area, because the body is closed, and the body has a volume omega, you have to show that the left hand side is equal to 6 times the overall volume. So we have to show that this is equal to finally 6 times the volume of the body. So let's see how we proceed. So the first thing we do is we simply apply initial notation, which makes our lives much more easier. So the initial notation for x dot x is simply xi. We already have discussed many times, so there's no point discussing it again. So dot product between two vectors, in this case both are x, is xi. Then there's a gradient of that. So xi is simply a scalar. So gradient of scalar, as you know, was something comma j, and then this whole thing is dotted with n hat. So that means that you have an nj here. So you can go a bit slow, and then you can take this as two vectors with ej, ep, the way we've done it earlier, but ultimately you end up getting the same form. As you can see that finally this whole quantity is a scalar because it's a dot product between two vectors, and we can see that the quantity that we have got here is also a scalar because it has no free indices. It has two indices, I and j, and both are repeated. All right, so this thing is integrated over d gamma. Now we can apply the Gauss divergence theorem. So what that says is that this integral is equal to the volume integral So I'll quickly, for a quick recap, I will write the Gauss divergence theorem here. Or just the Gauss's theorem, the general one. Let's call this M. Otherwise, there's a confusion. All right. So as per the Gauss's theorem, in our particular case, T ij dot m in this case is equal to xi comma j, and our index q is the same as index j. So if we make these changes and apply the Gauss's theorem the way it's written in the black color, then we get this expression here. Okay. So now we simply have, we just have to simplify things. So let's expand the first bracket. So when we do that, what we get is xi comma j times xi, and that's twice of that. Okay. So xi times xi whole comma j becomes xi times xi comma j, and then the second one becomes xi times xi comma j. So you add them, you get twice of that. Okay. Now if you remember that xi comma j was nothing but the Kronecker delta, because x here is the position vector. So when we make that simplification, that's what we get. Now 2 is simply so xi times delta ij. Now we can use the substitution property of delta, so this becomes twice xj. So we use the substitution property of delta, and this becomes twice xj, and this whole thing is comma j. So this simply becomes, now 2 is simply a constant, so we can take the 2 out of the integral and the brackets as well, and thus we get xj comma j d omega. Now again we know that xj comma j is nothing but delta jj. Okay. Now delta jj is not dependent on the elements, so this integral is happening over a small d omegas. So we can see that delta jj has no dependence on the position vector here, so we can take this out as well. Right. So delta jj, as we know, is 3. So 3 times 2 is 6. So this becomes 6. And integral of d omega over the whole volume omega is nothing but omega. So that's the proof. Is that clear? Does anyone have a question? Okay, if there's no question, then we'll move on. So coming back to today's lecture. So let's start with a quick recap of what we've been doing in terms of the stress tensor definition. We'll recap two things. One is the Cauchy stress principle, which is a very important principle that helps us define the traction vector T hat and also the state of stress. So we talked about a special vector T hat, but this vector also has a normal associated to it. So it's a vector which is associated to another vector. So we'll discuss that, we'll recap that. And we also talked about the state of stress in the last lecture, which was an infinitely long list of normals and stress vectors. And then we talked about the good news that we don't need to store infinite information. We can create the infinite amount of information from finite amount of information. And then the second thing we'll recap is the Cauchy stress formula, which is given here. So let's quickly go back to the last the slides from last lecture, and we'll use that to recap, which will make our lives much easier. So last time we talked about, so we started with a body, and we said that let's hypothetically slice the body into two parts, parts 1 and 2, and the cutting plane, which is the plane that is used to slice the body, always passes through a point P, because it's the point P where we want to find the stress information. So when we do that, when we create that hypothetical cutting plane, and we only consider part 1, that is, we're trying to write the free body diagram of part 1. So what we do is we take a small area delta gamma star around the point P, and we find the total force acting on the small area delta gamma star, which we call as delta F. So the Cauchy stress principle states that as our delta gamma star tend to 0, the limit of the ratio of this small amount of force acting on that small area to the amount of the area tends to, it has a limit, and this limit is called the stress vector or the traction T. Now what we see is that it has a superscript n hat associated to it, and that is because we chose a cutting plane in such a way which had a normal along the direction n hat. So if we change our choice of cutting plane, then we get a different stress vector or different traction T. Next, we stated that we need something called the state of stress at the given point P. That is a list or the tuple of all the normals that can be drawn at point P and the corresponding stress vectors. Okay, this information can then be used by engineers to design structures. But this is infinite amount of information because this vector has infinite amount of rows, because you have infinite directions that can be drawn at a given point P. But then the good news was that we can create this state of stress using finite amount of information. So then what we said was that let us find the stress vector on 3 mutually perpendicular planes. So we had drawn 3 planes, the red one, which is perpendicular to E1, then the green one, which is perpendicular to E2, and the black one, which is perpendicular to E3. So once we draw these three planes, we try to find the traction vectors on these three planes, which is given here. And then we said that using the information available on these three planes for the stress vectors, we'll try to find the stress vector for an arbitrary plane on an in hand direction. Sorry. So this is what the Cauchy stress formula is. So this states that we can find the traction vector on an arbitrary cutting plane in the n hand direction using the stress vectors on the Cartesian planes and the normal n hat. So if I give you the 9 components, which are the 3 rows of this matrix, and I give you the 3 components of the normal, then you can use that and create the 3 components of the stress vector on the n hat direction plane. So this is a very important formula. It's called the Cauchy stress formula, and this is actually used to define the Cauchy stress tensor. So the stress tensor sigma, which is called the Cauchy stress tensor, is defined as this. Okay, so once the Cauchy stress tensor has been defined, we can rewrite this Cauchy stress formula in this second form, which uses the sigma ji or the Cauchy stress tensor in it. So that was a quick recap of the lecture from last week. Is that clear? Any questions on that? All right. So the next question was, is the stress matrix actually a tensor? Okay. So let's show that today. So is the stress actually a tensor? So I've already written the solution, well, most of it, and we'll be going through it. So that saves us a lot of time writing that in the video. So is stress actually a tensor? So the way we proceed is first we draw our body. So we have the part 1 the way we had drawn earlier, and we have a point P as we have written here, and we have a hypothetical cutting plane, and the cutting plane has a normal with the normal given as in the n hat direction. Okay. And at the point P, we have a traction vector which is given as T superscript n hat. Okay. So we'll be using this in the context of showing stress matrix as a tensor. Now, on the left hand side, we have the traction vector T. Now we can write the T vector as Ti Ei, right? So we are writing that in terms of its components in the 3 mutually perpendicular Cartesian directions. Now, if you look at the Cartesian axes on the bottom right, we've drawn a blue one, which is x1, x2, x3 centered around P, the point P, and we have a green one, which is the primed axis, which is or the rotated axis in this case. So we can also write our stress vector T in the prime coordinate system. That is, we can write that as Ti prime, which is the components of the stress vector in the 3 primed Cartesian axes or the green axis. So Ei prime is are the unit vectors in the green coordinate axis. So we can write that. Now, as we just saw using the Cauchy stress formula, that we can write Ti as sigma Ji and J. So it simply follows from the Cauchy-Stress formula. So that's what we do. And again, in the green axis, we can write Ti prime as sigma Ji prime Nj prime. Again, Nj prime is the primed representation of the normal vector. Okay. So next, what we do is we use our vector transformation properties. We still cannot use the tensor transformation property because we don't even know if stress is a tensor. But we definitely know that our Ei prime is a vector. If it is a vector, then it transforms like a vector. So we can write it as AIQ EQ, where EQ are the unit vectors in the non-primed axes. Similarly, our normal is also a vector. So we can use the vector transformation rule to write Nj prime in terms of NP. So the next step is simply substituting these Ei prime and Nj prime into equation number 1, which is given here. So when we do that, we get sigma Ji Nj Ei, which is same as the left hand side earlier, and the right hand side, this is the left hand side. In the right hand side, now we're going from here. So the right hand side becomes, well, this is sigma Ji prime as it is, or Nj prime becomes AJP NP from number 2, and our Ei prime becomes AIQ EQ from number 2. Okay. Next step is simply to rearrange the terms on the right hand side. So we just take the A matrix terms on the left hand side, and left hand side is on the left, and rest we keep to the right. And then what we see is on the left hand side we have sigma Ji Nj Ei, same as earlier. But if you see this term on the left hand side, J and I are both dummy indices. So I can very well replace J with P and I with Q. So if we do that, we can actually do that here. Right. So now what I see is that NPEQ and NPEQ are common on both sides. So now I can take everything onto the left hand side, and that gives me this final form. And please note that right hand side is a 0 vector because the left hand side is also a vector. So it has 3 components on the right hand side as well, where each component is 0. So if we see this equation, then of course what we see is that the three terms, the 3 components it has are all zeros. But if you look at the components, remember the choice of the normal vector n hat was arbitrary. The reason being that we chose a cutting plane arbitrarily. Now we could have very well chosen another cutting plane. So this n hat, this thing is arbitrary. So what we are saying is that this bracketed terms times NP is 0, but NP is arbitrary. So NP need not be 0. So that means the bracketed term has to be 0 identically. Okay. So since the choice of n hat was arbitrary, so we can write the bracketed term is 0, or when you rearrange that, you get sigma PQ is AJP AIQ AJI prime. Right. And if you remember, then this was the tensor transformation property. or in the symbolic notation, we can write this as sigma is A transpose sigma prime A. Okay, so this was the transformation rule for second order tensors. Now, since sigma satisfies this property now, so we can say with confidence that sigma is indeed a tensor. It's very important to understand how to show if something is a tensor. So for something being a tensor, we have to show that it satisfies the tensor transformation property. So we did not assume it satisfies. All we assumed was that the vectors in the expressions in the beginning were satisfying the vector transformation property, which of course is true because we already have assumed or accepted the fact that n hat and ei prime were vectors. But using that and the definition of the Cauchy stress tensor, we were able to show that sigma is indeed a tensor. All right, so I'll ask you to try example 331 from book, which which simply gives you a stress tensor sigma and asks you to find the traction vector on a given normal direction using the Cauchy stress principle. Any questions? All right. So there's a very common representation of stress called the cube representation of stress. So what we do is, it's simply a way to represent the different terms of the stress tensor sigma. So what we do is we draw the Cartesian coordinate axis. And then we draw a cube Okay, so remember that the definition of Cauchy stress tensor is that sigma ji is TIEJ. So what that means is, if I take one of the planes, which is the plane which has got E1 hat as its perpendicular, so that is this plane, which has a normal in E1 direction. Well, sorry. So if we do that, then then the stress vector which I draw on this plane it will have three components. So I can write that as T1, so I can write my stress vector on this E1 hat plane with the three components T1, T2, and T3 on E1 hat. So what that means is, if I try to draw these three components, then one of the components is along E1 because it's the first component. And there's one component which is along E2, and there's one component which is along E3. So this is my T2 E1. This is T3 E1, and this is E1 E1. So on every plane, we can draw three components. And if you see the definition of stress tensor, then these terms actually are sigma 1, 1, so this is simply taking the definition from above. So sigma 1, 1, sigma 1, 2, and sigma 1, 3. So what we say is that sigma 1, 1 is this is sigma 1, 1. This was sigma 1, 2, and this was sigma 1, 3. Okay, similarly, I can draw three more planes. And what I ultimately see is that I have my sigma 1, 1. Sigma 1, 1, sigma 2, 2, and sigma 3, 3 are normal stresses because they are in the direction of the normal of the plane, and the rest ones are always in the plane or shear stresses. Okay. But please remember that sigmas are nothing but they are the components of the stress vectors in the Cartesian coordinate axis, and everything is defined at a given point. So using the cube representation, sometimes we confuse ourselves by saying that things are defined on three different planes at three different places. So these three planes actually pass to the same point P, and it's at point P that we are considering all the information. But since it is difficult to show everything at a given point, so we tend to draw a big cube, and then we show that over three different planes of three different planes that don't intersect at a point. But actually, everything is at a given point P in different directions. So this is called the common, this is known as the common cube representation of stress. If you want, I can draw the other ones as well, but that becomes quite congested here. So please consult the book if you want to see more about this, but I would suggest that if you can, you don't need to use this representation. It simply confuses us sometimes because of all the planes not intersecting at the given point P. All right, so, so we'll move on. Sorry, the next topic. So next topic is the force and moment equilibrium, which is this one. All right. So we say that a body is under equilibrium if both the net force, the external force is 0, and the net moment acting on the body is 0 at a given point. In fact, at any point. So you take the moment at any point, and it should be 0, and then we say that the body is under equilibrium. So what we'll do is we will take again our body hypothetical our body omega, and we'll try to write the force equilibrium equation on that first. Now remember that we said that we can characterize the forces as either body forces or surface forces. So that's what we do here. So we say that the integral of all the sum of all the surface forces and the body forces is 0. The surface forces, as we know, can be written using T, okay, traction, and the body forces are represented using the body force per unit mass, which gets multiplied by the small mass element, which is density times d omega. Okay. So what I can do is I can write, so this is d omega, and so if I look at the first term here again, then the integral is a closed integral. So that is on the surface of the body here. So the integral happens on the enclosing surface of the body that we have here. So in this case, I can write the integral over gamma as the integral over the small elements d gammas, and the stress, the traction vector denotes the force acting on the surface. So what you have to do is you have to integrate over all the traction vectors on the surface gamma. And the next step is to integrate over the complete volume, which we do that by taking all the volume elements d omegas inside the body. Okay, so this is the complete body that we've taken. All right. So now what we can do is we can use the Cauchy stress formula. That is, we can write the traction vector in terms of the stress tensor. Right. And we can also apply the Gauss's theorem or the Gauss divergence theorem. So that helps us to convert the first integral into volume integral. All right. So when we use this into the expression above, so we get okay. So that's the integrated form of the force equilibrium equation. Now we had taken the complete volume as the omega volume that we started with, but we could also have started with a part of the body. So instead of taking this whole body, we could have started with some part of the body, and we could have applied the Gauss-Divergence theorem, the force equilibrium over it, because every part of the body individually is also under equilibrium. Okay, so there's no part of the body which is accelerating. The complete body is under equilibrium. So we can take small sub-volumes or subsets of the body, and we can apply the force equilibrium equation on these subsets of the body as well. Okay, so if we do that, what we realize is that the choice of this omega here is arbitrary. So what that means is that this term here has to be 0, because if the choice of omega is arbitrary, then the thing that is being added has to be 0 individually. So this gives and this equation is called the local equilibrium equation. Right? Any questions? Okay. The next step is to write the moment equilibrium. Now it's very similar. The process is very similar, but still we have to go through it because the results are very interesting. So what we do is we find the net moment about the origin O, which may not pass through the body. So we have the body force acting on some element inside the body. So the torque because of that at point O. So for that we have to find torque using this. So when I write the moment equilibrium, it says that the sum of the moment about origin in this case is 0. So I can write that as and then we also have the surface force creating some torque. And this is equal to 0. So the torque of the body force and the torque of the surface force when you add them, all of them, you integrate them over the complete volumes and areas, this net moment about origin has to be 0. And the reason it's the moment about origin is because the position vector has been taken from the origin O in this case. Now we use indicial notation. So what we do is we write these equations in the indicial notation form. Okay, so the sum of these two is 0. Now, if we take the second one and simplify that, so what we have done is we have applied the Cauchy stress formula. So we have written our Tj at n hat. Remember, the Cauchy stress formula allowed us to write the stress vector on an arbitrary normal in terms of the Cauchy stress tensor and the normal NP. So we simply wrote Tj n hat as sigma Pj NP. You can consult the definition of the Cauchy stress formula or the Cauchy stress formula, and you can see that this is the case. Next step here is to apply the Gauss divergence theorem. So that allows us to write this in terms of the volume integral. Right. So we have to simplify the terms on the brackets. In fact, what we can do is we can substitute this as it is into this equation number A. So what we see is that this term xi comma p, this can be replaced by delta ip because x is our position vector. Right? So let's take everything inside one integral. Right? So what is this term? Now we just saw, if we just go back a couple of slides, this local equilibrium equation says that rho bi plus sigma ji comma j is 0. So what we see is that rho bj plus sigma pj comma p is nothing but the same as the equilibrium equation we had just written. So this thing is 0. So the only thing we are left with is epsilon ijk times sigma ij times d omega is 0. Okay, now using the same ideas as earlier, this omega, the choice of omega that we have here is arbitrary. So we can say that epsilon ijk times sigma ij is 0. So what does this tell us? I mean, what does this mean? So let's take k equal 1 here. So this becomes epsilon ij1 times sigma ij is 0. Now we know that I and j are dummy indices here, so we can expand them. In fact, if you expand this whole term, and since we already know that epsilon is 0 if any of the indices repeat, then the only indices we can have here are epsilon 2, 3, 1. Sorry. So that's the expanded form. And we already know that epsilon 2, 3, 1 is 1. So this becomes sigma 2, 3. And epsilon 3 to 1 is minus 1. So this becomes -1 and this is 0. So that tells us that sigma 23 is equal to sigma 32. We call that 1. And now if you put k equal to 2, what you get is sigma 13 is equal to sigma 31. So these tell us that sigma ij is equal to sigma ji, or sigma is symmetric. Okay. So let's stop here, and we'll talk about a bit more detail on sigma being symmetric and its effects in mechanics in the next class. So before we close, any questions? All right then, there's no questions. So thank you very much. I'll see you on Wednesday.